Again, welcome to Statistics. This is DSRT 734 class. In this lectures, we're going to start with F distribution, compare it to variances. So again, compare it to variances. Our main objective here is to interpret the F distribution and use an F table to find critical values and perform a two-sample F-test to compare two variances. So we start with the F distribution. Here they say let x1 square and s2 square represent the sample variance of two different populations. So again, s1 square is a sample variance, s2 square is another sample variance for two different populations. Now, if both populations are normal and also the population variances are equal, then the sample distribution of F is equal to S1 squared divided by S2 squared. Again, S1 is the variance for the first, again, sample, the sample variance for the first population, and S2 squared is again the sample variance for the second population. So here we are saying that if the two populations are normal and also the population variances are equal, then the sample distribution F is equal to S1 square over S2 square. Here again, we are saying that the two population variances are equal. And we collected a sample from these two populations, and their variances, which is S1 square and S2 square, represent, again, the two different populations sample variance. Now, if the populations are normal and the population variance also are equal, then the sample distribution of F equal to S1 square divided by S2 square. This is called the F distribution. So what are the properties of the F distribution? Here we said that the F distribution is a family of curves, each of which is determined by two types of degree of freedoms. So F distribution is a family of curves, each of which is determined by two types of degree of freedoms. And we have the degree of freedom for numerator and degree of freedom for the denominator. So the degree of freedom corresponds to the variance in the numerator, and this will be denoted as df and uppercase N. So this is again degree of freedom for the numerator. Then we have the degree of freedom corresponding to the variance in the denominator. Now, in order to use the F table, we need to find the degree of freedom for the numerator and then the degree of freedom for the denominator. So F distributions are always positively skewed. F distributions are positively skewed. And also the total area under each curve of an F distribution is always equal to 1. So the condition here, in order to say F equal to S1 square over S2 square, S1 square will be the variance, the sample variance for first population, and S2 square will be the sample variance for the second population. In order to say that F equal to S1 square over S2 square, there are some conditions, as we saw earlier, we have to meet. And one of the conditions is that the population have to be normal, and also the population variances for both two population variances must be equal. Then we have the formula F equal to S1 square over S2 square. Now, the properties of F distribution, we say also here, F values are always greater than or equal to 0. And we know the total is 1. Then for all F distributions, the mean value of F is approximately equal to 1. For all F distributions, the mean value of F is always again approximately equal to 1. So for example, here we have a degree of freedom, the numerator equal to 1, degree of freedom, the denominator is equal to 8. And this will be our shape of curve. Then here, if the degree of freedom, numerator equal to 3, degree of freedom, denominator equal to 11, we have different shape here. And also degree of freedom n equal to 8, and degree of freedom d equal to 26. Again, n represent the numerator and the d represent the denominator. So the critical values for F distribution, as usual with the chi-square table, we still have to know the alpha. So first, in order to find the critical value is very important because that's the main region that will divide the acceptance of HO or the rejection of HO. So as the hypothesis testing for F distribution, comparing variances, the steps are almost the same as, again, the chi-square for independent testing for two variables. So in order to get the critical values, we have to specify the level of significance. Always is given. But this time we need to determine 2 degrees of freedom. First, we determine the degree of freedom for the numerator. Then we need to determine the degree of freedom for the denominator. Then from there, we use the F distribution table or the F table. So yeah, we said table 7. Table 7 again is the F table. So we use the F table to find the critical value. If the hypothesis testing is 1 tail, then we use the full, again, alpha is the level of significance. So if I'm doing 1 tail, I will use the alpha value for the F table. So the same concept as chi-square. In order to find the F value or use the F table, we need a degree of freedom for both the numerator and the denominator. Then also we need the alpha or the level of significance. Now, if it's a 2-tail, we divide the alpha value into 2. Remember, we did the same thing in our previous hypothesis testing. If hypothesis test is 0, let's say the alpha is 0.05, and I'm doing 2-tail test, I will divide 0.05 by 2 and get 2 parts. So the same concept here. So now let's go through an example here. Here our example says find the critical F values. Here we are going to find the critical F value for a right tail test when alpha equal to 0.05, degree of freedom n equal to 6, and degree of freedom d equal to 29. So here they gave us all the 3 values. So we can go ahead and find the critical value. So in this case, this is how our F table looks like. We can see the degree of freedom for denominator is the row values. Then degree of freedom for the numerator is the column values. So here we look at our value first. And also we have the alpha. We are in the section of 0.05. There's a section for, again, this table will continue the section for 0.10, etc. So let's look for the degree of freedom for the numerator first. And the numerator will be 6. So we are in the 6th column here. Denominator is 29, so I'll go all the way down to 29. So the value will be somewhere around, I think, 2.43. But let's see. So degree of freedom for numerator is 6. Degree of freedom for denominator is 29, so it's 2.43. And also the alpha is very important. So we are in the area of alpha equal to 0.05. So this means the critical value is F0 equal to 2.43. So next, again, find the critical value for 2-tail. Again, the previous one we did is a 1-tail. Now, if we want to find 2-tail, we're going to divide the alpha by 2. So we have our degree of freedom for the numerator, which is 4, degree of freedom for the denominator, which is 8. Alpha is 0.05. So solution, first, when performing a two-tail hypothesis testing using the F distribution, you need only to find the right tail critical value. So we need to find only the right tail critical value. But as we said earlier, we still divide the alpha into 2 because we are doing two-tail. So yeah, our alpha value will be 0.025. I think that's the most important part. This two-tail, whatever alpha value we have, we divide it into 2. So we go back to the table again. This time I will go to the area of 0.025. So we can see we are in the area of alpha equal to 0.025. Then the degree of freedom for the denominator is 8. So I'll go to 8 and I'll go to 4. So we are in 4 and we are in 8. So our answer will be 5.05. So these two examples teach us how to use the F table to find a critical value. Again, we need a degree of freedom for the denominator, degree of freedom for the numerator, and also the alpha value, the level of significance. So next, we are going to do the TwoSample Ftest for variances. Now here we say that to use the TwoSample Ftest for comparing two population variances, the following must be true. First, the samples must be randomly selected. The samples must be randomly selected. Then 2, the samples must be independent. The sample must be independent. Then each population must have a normal distribution. Again, here we have two populations. We are comparing two population variances. So that's the step, the test statistics. We look for the F value, which is S1 squared divided by S2 squared, which will be the sample variance for the first population and the sample variance for the second population. So here we say where S1 squared and S2 squared represent the sample variance with S1 squared greater than or equal to S2 squared. So then next we need a degree of freedom for the numerator. It's normally N1 minus 1. And N1 is the size of the sample having the variance of S1 squared. So again, the degree of freedom for the numerator will be the sample size, N1 minus 1. Then degree of freedom for the denominator will be the second sample size, N2 minus 1. And here we say the N2 is the size of the sample having the variance of S2 squared. So again, here we find the degree of freedom for numerator, the size of the first sample minus 1, degree of freedom for the denominator, the second sample size minus 1. So let's see this in words and also in symbol. Again, this is hypothesis testing. So the first thing we need to do is to identify the claim. So we are going to state the null and also the alternative hypothesis. So here they say state the HO and HA. Then second, we have to specify the level of significance. We need to identify our alpha. Then after that, we identify the degree of freedoms. So the degree of freedoms is N1 minus 1, N2 minus 1, which is the degree of freedom for numerator, then degree of freedom for the denominator, which will give me N1 minus 1, N2 minus 1. Then we determine the critical values. Again, when we know we saw how, again, we went through these steps when we are looking for the critical value in our previous two examples. So again, in order to get the critical value, we need the alpha, we need a degree of freedom for the numerator, then the degree of freedom for the denominator. Then we use the F table to find the critical value. So if we know the critical value, then we can determine the rejection region, because the critical value separates the rejection and accepted region. So in order to do that, we calculate the test statistics. So when we calculate the test statistics, the F value that we get, if it fails in the rejection region or acceptance region, then again, when I say rejection of HO or acceptance of HO. So we can see that, as I said earlier, the steps, again, here we have new formulas and we are testing different things. We are not testing if two, for example, two variables are independent. No, here we are testing if two sample variances or the variances are the same or not. But what I'm trying to say, hypothesis testing, the steps are always the same. First, we have to determine our claims, for example, the HO and HA. Then second step, we get our level of significance. Then the third step, I need the degree of freedom. Now, when I have my level of significance and degree of freedom, if it's chi square or t square, I can find my critical value. But with F distribution, we need two degree of freedom value. The degree of freedom value for numerator and the degree of freedom value for denominator. So now we have the alpha level or the level of significance, which is the alpha. Then we have the degree of freedom for numerator, degree of freedom for denominator. With these three values, we can find the critical value. So after we get a critical value, then we can determine, we can draw our diagram and determine the rejection region. The next step is to calculate the test statistics using the formula given to us, S1 square over S2 square. S1 square must be greater than or equal to S2 square. So after we find the F, then we can make a decision to reject or fail to reject the null hypothesis. Again, depends on the value of F, whether it fails in the rejection area or acceptance area. Then we interpret the decision in the context of original claim. So we can see that, again, the hypothesis testing for most of all the tests we have done, the steps are the same. Only that formulas change because we are testing different things or different types of variables. So let's see the example here. The example here said a restaurant manager is designing a system that is intended to increase the variance of a time customers wait before their meals are served. So here again, we are trying to test the variance. We know the concept of a variance is the variation of our data. For example, if we have two customers, or let's say we have three customers, maybe customer 1 wait for only 2 minutes, customer 2 wait for 10 minutes, customer 3 wait for 3 hours. So we can see the variance are not the same. Or we want to test if customer 1 wait for 1 minute, customer 2 wait for 1 minute, customer 3. So we can say that the variance are the same. So here we have a restaurant manager is designing a system that is intended to increase the variance of the time customers wait before their meals are served. Under the old system, the random sample of 10 customers had a variance of 400. Under the new system, the random sample of 21 customers had a variance of 256. So we can see that again, everything fall in place. We have two populations now, two different systems. And also they gave us two different values for the N1 and N2, 10 customers, 21 customers. And also they give us alpha. So by going through the steps for the hypothesis testing for comparing two variances from two different populations, we can see that this question meets all our conditions. Again, the restaurant manager is designing a system that is intended to decrease the variance of time customers wait before their meals are served. Under the whole system, the random sample of 10 customers, so we can say N1 is 10, and it had a variance of 400. So our first variance 400. Then under a new system, the random sample is 21 customers, which means N2 is 21, had a variance of 256. So we can say S2 square is 256. The first S1 square is 400. Remember, even our condition said S1 square should be greater than or at least equal to S2 square. And also alpha is given to us. Now we want to do our hypothesis testing to check if there's enough evidence to convince the manager to switch to the new system, assuming both populations are normally distributed. So again, first we check, is N1, you see here we have 400 greater than 256. We have N1, we have N2, we have S1 square, we have S2 square, we have the alpha. So we can do this test. So our condition said, okay, is S1 square greater than or equal to S2 square? Yes, okay, then we can continue with our testing. So now we say the population variance of the first population should be less than or equal to the second population variance. Because here, based on the question here, we want to test, is there enough evidence to convince that the manager to switch to a new system, assuming the population are normally distributed? Because when we see the new system variance is lower, 256, the old system variance is high, which is not good because some customer will wait for very short, some customer will wait for very long. We want, hopefully, customer, even if the variance can be 0, that would be perfect. Customers wait at the same time. So that's why we say, okay, the first system, which is the population, first population, variance should be less than or equal to the second one. Or the first one should be greater than the second one. So this is our test we want to do. Alpha is given to us 0.10. Now we were able to find the N is 9, and then D is 20, because we have 10 and 21. And when we go back to the question again, the first sample size is 10, the second sample size is 21. So which means we get 10 minus 1 is 9, 21 minus 1 is 20. So 10 minus 1, 21 minus 1. So now we have all our three values here. Alpha, degree of freedom for numerator, degree of freedom for denominator. So we can find the critical value and draw the rejection. When we look at the critical value, we get 1.96. And that's where our line comes in. So this to the left of 1.96 will be a accepted area. To the right of 1.96 will be rejection. So we have our values now. The next, let's find the test statistics, which is S1 square over S2 square, which gives us 400 divided by 256. So that gives us 1.56. 1.56 went to the left. So which means we are going to fail to reject HO. We will accept HO. So HO states that, then now we have to state our decision. When we look at HO, we say that the population, the first population sample, which may be the old system, is less than or equal to the second population. So here we say there's not enough evidence to convince the manager to switch to the new system. We can't switch to the new system. Why? Because basically we fail to reject HO, which means the old system, the first population, variance is less than or equal to the second. And the goal of this, when we are testing a variance, we know a variance or standard deviation tells us how the data values varies. Now, if I have a restaurant and I have 2 customers and their waiting time, the variance is high, it means one customer waited very short time, another customer waited very long time, which is not a good system for a restaurant. we want all the customers to wait approximately the same time, or maybe roughly a little bit different, but not too much. So that's the test we did here. Now let's try this second test. Here they say we want to purchase a stock in a company and are deciding between two different stocks. Because a stock's risk can be associated with a standard deviation of its daily closing prices, you randomly select samples of the daily closing prices for each stock to obtain the result. At alpha equal to 0.05, can you conclude that one of the two stocks is a riskier investment, assuming the stock closing prices are normally distributed? So we have the stock A, we have N2 is 30, S2 is 3.5, stock B, N1 is 31, S1 is 5.7. So first we check, we see if S1 square is greater than or equal to S2 square. Yes, we can see. So if that's the case, we have all the values that we can. We have N1, N2, S1, S2, and we have the alpha also. So we can do this test. So we start the steps again. First, we say, okay, is 5.7 square greater than 3.5 square? Yes. So S1 square is 5.7 square. S2 square will be 3.5 square. Now we state our HO. Remember the question said if they are equal. So here we say HO, the first is equal to the second, or I'll say the population, the first population stock variance is equal to the second population stock variance. HA will go against it. So if it's equal, then not equal. Our previous example, we say if it's less than or equal, then HA will be greater. And if we have greater and equal, then HA will be lesser. So as we said earlier from beginning of hypothesis testing, HA is always against HO. So here we are doing two-tail if it's equal. So you can see we divide our significant level into half. So we get 0.025. In the questions, the significant level is 0.05. So here it becomes 0.025. Then degree of freedom for the numerator is 31 minus 1. Degree of freedom for the denominator is 30 minus 1. So we have 30 and 29. Okay, so we have the three values now. We have the alpha, we have the degree of freedom for numerator, we have degree of freedom for the denominator. Then we can plot our rejection and accepted region. So we look for our F value. Again, when we look at our F table, our F value, the critical value will be 2.09. So 2.09 to the right or to the left. Left of 2.09 means we accepted HO. To the right of 2.09 means we rejected HO. So we do our test statistics. We divide the F by, F equal to S1 square divided by S2 square. So it will be 5.7 square divided by 3.5 square. And that gave us 2.65. So we said that 2.65 went to the blue area to the right of 2.09. Okay, so this means again we are going to reject HO. So reject HO. There's enough evidence to support the claim that one of the two stocks is a riskier investment. They are not the same. So this will be the conclusion of our lectures on, again, F distribution and also doing F tests to compare two variances. Again, we did two examples. First, we learned how to find the critical value using the F table. Then from there, we do the hypothesis testing for two variances from two populations using the F table. As we said, we can see that the steps are the same in any hypothesis testing. The only difference is since we are testing different variables or different concept, formulas changes. We saw the chi-square, the steps are the same as F distribution. So in F distribution, first again, hypothesis testing, we are going to state our HO and HA. Then the second step, we have to know our level of significance, which is the alpha. Then the third step, now this is again F distribution. So we need 2 degrees of freedom. Degree of freedom for numerator, degree of freedom for denominator. Now, if I have degree of freedom for numerator, degree of freedom for denominator, and also the alpha value, then I'll be able to find the critical value. Then I can know the region for rejection and acceptance of HO. Then next, I'll do the test statistics. I'll find the F value. The F value is S1 square over S2 square. Then when we get the value, we see whether it goes to the left or to the right of the critical value. To the left means we accepted HO. To the right means, again, we reject HO. So again, wish everybody the best and wish to see you in the next lectures. Thank you. Bye.